wonderful conference and actually inviting me to be part of this conference. So I'm going to talk about Majorana bound states in 1D superconducting nanowires transport and braiding. I'm Suhas Gangadharia from the Department of Physics, IISER Bhopal. The architect of this work is my graduate student Dibajyoti Sahu, who just graduated. And this talk would be based on these two works. One of them is published. The other one, we hope to send it to archive in maybe 3 weeks or so. So the outline for my talk would be as follows. I will first consider just simple Majorana modes, discuss Kitaev 1D chain, and I will briefly discuss Majorana end states for quantum computation. And then I will come to our work, which is the finite time control of Majorana bound state dynamics. What we want to do is we want to basically move the Majorana and braid the Majorana. And basically we are going to investigate this process by studying the many body ground state. We will also study the effects of temporal noise on finite time Majorana transport, excitation generation, and the fidelity of topological operation. We'll show that while braiding or moving these Majoranas, there are two possibilities. One, either we can do it very fast, a fast braiding or manipulation of the Majorana results in a lot of excitations. However, fast movements are typically immune from noise-related errors. The second one is slow errors. Adiabatic evolution. The adiabatic evolution actually does not result in diabatic errors, but it is susceptible to noise-induced errors. So there is a competition whether one has to go fast or slow. That's what we are going to discuss a bit. Okay, so let's consider the usual Majorana modes in condensed matter. Consider superposition of particles and holes, which is given by this expression. Now, if alpha is equal to beta star, then you have this gamma would be equal to gamma dagger, which is the standard definition of this Majorana mode. Now, these Majorana modes would naturally be, the natural playground for these modes are in superconductors, where the excitations are described by Bogoliubov quasi-particles, which are basically superpositions of particles and holes. So it's of this form. And however, so this has the structure similar to here. However, this gamma epsilon is not gamma epsilon dagger in general. However, it turns out that due to the particle-hole symmetry of the Bogoliubov-de Gennes equation, there is a relationship between this gamma operator with energy mode E and the gamma operator with minus energy E. So they are related via this relationship. Now, if E is equal to 0, if there is a state for which E is equal to 0 state is allowed, for that, that state would be the Majorana mode. Okay. These Majorana modes cannot be present in a S-phase superconductor, simply because here the particle-hole linear combinations are formed out of different spin species, while it can be present in a P-wave superconductor because these particle-hole species are formed out of the same, they belong to the same species. So on the other hand, S-wave superconductor, spin orbit, and magnetic field can combine together to give an effective P-wave superconductor, and a Majorana mode can be possible. Okay, so I will briefly go through this standard example of Kitaev 1D P-wave superconductor, which includes a tunneling term, a superconducting term, and a chemical potential term. In the continuum limit, this can be expressed in terms of this block BDG Hamiltonian, which is described compactly in terms of this block vector. The magnitude of the block vector gives the energy spectrum. Then there are two regimes. One corresponds to chemical potential greater than 2T, and another is chemical potential less than 2T. In both cases, the energy spectrum looks the same. However, if one plots this block vector for k going from, let's say, 0 to 2 pi, one sees the difference that in one case the winding number is non-zero, while in the other case winding number is 0. So the case where winding number is non-zero, it belongs to, this system would belong to the topological it would be called as a topological superconductor, and if you cut the wire, then the ends of the wire will basically host these Majorana modes. Now if while tuning, let's say the phase, let's say we can always tune the phase to go from trivial to topological phase by tuning some of the parameter, like for example, I can tune my chemical potential and reduce with respect to the hopping term. What one finds is that going from this trivial phase to the topological phase, one would always encounter a band closing. Now this particular discussion is important because what we will be doing is we will be moving the Majorana modes, and when we are moving the Majorana modes, we will be tuning locally some of these parameters, and therefore the energy bands can come really close to each other, and then excitations can happen. Okay, so this is the once again a Kitaev's 1D model. I will just go through Kitaev's quick explanation for the origin of these zero modes. So what he did was express these fermions in terms of each individual fermion is expressed in terms of 2 Majoranas, and for some special case which belongs to the topological criteria, this special case is when the superconducting term is the same as the tunneling term and chemical potential is 0. In this case, the Majorana modes completely decouple, and these are the ones that we are all interested in. Now, in principle, what one can do with them are the following. So what we can do is we can combine two of these Majorana modes to form basically a non-local fermion, and this non-local fermion can be either empty or filled. Okay, and these are very robust because these fermions are non-local, and so local perturbations do not change anything. And basically, because of that, one can use it to store information. Moreover, what one can do is just, it was shown that if you just take these 2 Majoranas and exchange their position, this is equivalent to performing a unitary operation. And basically different combinations of these unitary operations can be used to form gates for quantum computation purpose, except for this T gate. Okay, however, there is a problem here. These 2 states cannot be used to form qubit because they belong to different parity sector. So what one needs to do is one needs at least 4 Majorana modes. If you have 4 Majorana modes, you can have 4 fermions, and with the 4 fermions, your ground state manifold would be 4-fold degenerate, in which 2 of them are even parity and 2 of them are odd parity. So you can form a qubit out of the even parity sector, for example. And if you perform some kind of a braiding, like let's say if you go from gamma 2 to gamma 3, this particular state will get modified. Okay, so now I come to my basically our work. So what we consider here is quantum wire in the T-junction geometry. So this is a very standard geometry which was initially proposed for the quantum computation purpose. And what was basically proposed that in this geometry, one can basically exchange this gamma 1 and gamma 2 positions. Okay, so that would be called the braiding. Now, the most minimum thing that one needs to do is to move basically the Majorana, which is, let's say, at one point to another point, let's say from here to here. And this can be done by, for example, changing here there is this chemical potential. By changing the chemical potential here, bringing it to the non-topological regime, one can move this Majorana from here to here. So the obvious question is, at what rates can we move this so that we don't accumulate too much noise? And what about the presence of, noise or environmental effect? Does it lead to error generation? Okay, so these are the type of questions that I want to address. So more specifically, the aim is the following. In the first part of my talk, to move the Majorana in a finite drive time. So I want to move from here to here. So when I want to study what happens to the new system, what I'm going to do is I'm going to study what happened to my basically the ground state when these things moved. So I'm going to compare the old ground state, which is now evolved into the new position. with the instantaneous ground state. And basically with that I will study the excitations which are generated. We will be using a piano key setup in which a certain region of basically the wires are split into different regimes, and at a time one particular, for example, regime's parameters are changed. Okay, so finally okay, so coming to the main part, so what we are interested in is this overlap of two wave function. One of them is the evolved ground state, so and while this one is the instantaneous ground state. So basically you had a ground state here, you kind of evolved and you reach this position, but this position, if you calculate your Hamiltonian, it will have some instantaneous ground state. You want to compare it with that. 1 minus of this fidelity gives you basically the defect generated. Now to do this, what one does is, I guess there should not be any dots here for whatever reason there is. One finds what is the initial ground state. The initial ground state basically satisfies this criteria where Bi's represents the Bogoliubov quasi-particles operators. So Bi's basically annihilate all of these, all the grounds. Basically, it annihilates the ground state. All the Bi's annihilate the ground state. And when you time evolve it, this psi state goes to psi t, while this Bi goes to beta t. And then you are going to compare it with, as I said, this instantaneous ground state. The definition of this instantaneous ground state is that it basically, when acted upon by the Bogoliubov quasi-particle, which is calculated for that particular instant, that it vanishes. Okay, so ultimately what we will calculate is this rather strange kind of thing. This involves a multi-point operator. So there are, as you can see, 2n of these and 2n of the daggers. So there are 4n operators. And these 4n operators are sandwiched between these two instantaneous, basically the bra and ket, the ground state, instantaneous ground state. It turns out that this strange looking expression is actually the same as this term. So to quickly explain that, so what you can do is you can here insert the identity, resolution of the identity operator, basically the set of all states which are 2 to the power of 2n in this case. The first state in here would be the evolved ground state, and basically the higher excited states are obtained from this evolved ground state by basically operating with one of these beta daggers. So all those states basically get annihilated because of these beta dagger. The only state which remains untouched is the ground state, and because of that all these things vanish, or basically they basically, you can say, it filters out only the ground state, and that's how you get this expression over here. Now to calculate this expression, one uses the Wick's theorem, where these big n-point correlators can be split into products of 2-point correlators. And basically these products of 2-point correlators can be expressed or written in a very compact form in terms of Pfaffian of this matrix A, which is an antisymmetric matrix. The terms of this antisymmetric matrix are basically the 2-point correlators. So we have broken down this rather difficult problem into products of 2-point correlators, but there is still some work to do here, that is to calculate these 2-point correlators, but one can do that numerically. I'm not going to go into the details of that, but I'll just tell you what the results of those calculations are. So one basically obtains this error, which is 1 minus the fidelity. So what one finds is that if one drives this over here, tau represents the drive time. So the shorter the drive time means you are driving it very fast. So if you drive very fast, the errors are very high. So these dashed ones are noiseless case. But if you drive it slowly, the noise gets suppressed. The errors get suppressed. On the other hand, if you turn on the noise, so the noise that we consider is telegraph noise, which there is some random fluctuations in chemical potential which goes up and down between two levels. We find that basically that after a certain time the effects of noise becomes important, and there is again an upturn or increase in the error generation. So these for each of these basically noise correlation time, there is one particular particular time scale which is the most appropriate, where the noise level is the least. We also considered what is the effect of noise correlation times. We find that at when the noise correlation time is very large, the noise generation or the error generation is less, whereas for very high this tau or correlation times, the error generations seem to also decrease. This could be due to some kind of self-averaging. So we also considered compared these results by our analytical approach, where these red bands represents the bands due to the lowest levels. While you are tuning the system from topological to non-topological, the bands will come down and will go up. So this can be treated in the Landau-Zener form, and we find that the error indeed shows an exponential suppression. For large times, large but finite times, it exhibits a 1 by tau square suppression. In the presence of noise, we followed this work, and we also showed that in the presence of diagonal noise, you have a linear upturn due in the error generation due to noise. Okay, so I will now come to the next part of my talk, which is the braiding. So once again, for a physical qubit, you need 4 Majoranas, and these are the ground state manifold. We will stick to the even parity. Now, as was discussed, if you exchange 2 Majoranas, this results in basically change in the wave function. Okay, so here I have exchanged this operator over here represents exchange of 2 and 3 Majorana. So this results in changing this state 0, 0 into state 0 and -1. So basically I call this as 0 and this one as 1. So this one is now transformed to a linear combination of this. If you exchange it once again, you go to this 1 state. Okay. So our question is, how robust is this braiding under dynamic driving? Okay, so let me just give you these 2 examples, 2 scenarios that we use for braiding. One of them is the well-known Alicia's braiding scheme, wherein you have this 4 Majoranas in this T-junction geometry. What you do is you push one of them, gamma 3, into this T-junction, and then you push gamma 2 onto this side, remove the topological regime so that this thing comes out, and then you push it back over here. So this would be one type of braiding. The second type of braiding has been also been of some vogue these days. This involves 2 wires, each of which has Majoranas at the ends, and in between there is a quantum dot. Okay, so this setup can be effectively be understood in terms of 1 quantum dot and 2 Majorana modes. Now this dot has only 1 Fermi level. If you have only 1 Fermi level, then it can be expressed in terms of coupling of 2 Majorana modes. Okay? And so what is done is to move, let's say, gamma 2, what you do is in the first step you want to move this gamma 2 into this region here. So what is done is you make the coupling of this quantum dot with the left side of the wire, which is this gamma 2. You slowly turn this on and while switching this off. And what happens is that the Majorana which was present here now moves about to the dot. And so what you have to notice is that in the whole process can be described by an effective Hamiltonian involving 3 Majoranas. This would be an antisymmetric matrix, which means that one of the state will always be at energy equal to 0. Okay, so now let's continue the process. Next is what you want to do is you want to move this gamma 3 into here. That is done by reducing the coupling here and increasing the coupling here, and so on and so forth. And this basically completes the braiding of gamma 2 and gamma 3 to gamma 3 and gamma 2. Okay, so the obvious question is, after braiding, so of course if it is a perfect braiding, then you go to 0 0, the 0 0 state goes to linear combination of 0 0 and 1 1 with these particular coefficients. The question is it, I mean, how can you check that it's a perfect braiding? Okay, so for that, what you need to know is how did the Bogoliubov vacuum, this is the initial state, it evolved, and how does it compare with the vacuum which is 0 and 1 1? Okay, so this is where you finally come to. You do the braiding and you stop at 0 0 and 1 1. So the next question, so the obvious question is, how do we construct the Bogoliubov vacuum? So the standard procedure is, or one of the standard procedure is, you basically take your Bogoliubov-Dejean's Hamiltonian, you perform this diagonalization via Bogoliubov transformation. So these D and D dagger operators are the ones which are performing that diagonalization, and the vacuum is defined by that state which annihilates all these decay states. Okay, so the vacuum of this Bogoliubov quasi-particle or Bogoliubov Hamiltonian is basically that state which annihilates all this decay. Now this can be actually created very simply if one thinks about it. What you can do is you can take the vacuum of the C operator, which is this O of C, and multiply it with all the decay operators, which is all the decays. And this would, and then this is indeed a vacuum. As you can check, you take any of the decay operator, there will be another decay present already here, and that will take it to 0. But the problem with this simplistic construction is that what can happen is that some of these decay state might actually annihilate the vacuum of the fermion itself. So then it's a problem, because instead of getting a state, you're getting 0. So to get rid of that problem, what you want to do is you want to get rid of those offending D operators, which basically acting on OC destroys it. Okay, so one of these approaches which I recently came across was this Bloch-Messier decomposition, discussed in this rather interesting book by Ring and Schuck. I think it's some nuclear physics book, and more recently it's been invoked in this paper by Mascott. So what they do is they decompose these matrices into rather unusual form in terms of these U bar, V bars and stuff, where it turns out that the V bars have these singularities. So you have to, basically in this notation, what you have to do is you basically have to discard the modes corresponding to these 0, or the modes corresponding to I. So here I and 0 have the same dimension. This direct something has the same dimension as this one has the same dimension as that one. Okay, so by discarding them, and in terms of these new operators, which I could call it as bar, you can form these many body vacuum states. The many body vacuum state will now no longer be 0 under any circumstance. Now this is the excited state, where you take this vacuum and excite by these two lowest lying creation operators. Now what you have to do is you have to sequentially take the overlap of these states with the evolved vacuum state. So this is the evolved vacuum state. And let me now just give you the quick results. So what we find is that, let's say you started with this vacuum state, and then after one exchange, what you should expect is that if your drive was kind of adiabatic, that you should find that the overlap of the evolved ground state with either 00 or 11 would be both half, and this is what is found, that after one exchange it's half, and then after another exchange, what you should expect is that the overlap of the evolved 00 state with 11 should be 1, which is what is seen here computationally, while it is 0 for the 00 state. And similar result is obtained for quantum dot, but of course in quantum dot there is, while here there is a sharp fall in between regions, in the quantum dot the overlap remains non-zero for certain regions. So here also what we find is that if we drive it really slowly, the diabatic errors are reduced. We believe that this some kind of flattening is an artifact. We are still working on it to see what is the reason for this flattening. And then we considered telegraph noise again in these scenarios, and what we found is that again, due to telegraph noise, there is an optimum drive time beyond which the error starts to creep. So for these are for different basically noise correlation times, and you see that the again noise, basically the error starts to creep up after a while. So slow drive in the presence of noise leads to enhanced diabatic drives, and we find that the optimal drive time for dot geometry is lower than for the T-junction geometry. So this is the optimal, this is for the quantum dot. So here this is, for example, the optimal time for it, which is something like 10 to the power of 2, whereas for here, for this one with the same noise correlation time, the optimum quench time is much larger. So one can, using the quantum dot, so main message is that with the quantum dot you can do the operations much faster. Okay, so here we considered noise in different regions of the wire, so in the wire 1, wire 2, and in T-junction separately, and in the global noise. Of course, if you have noise everywhere, that's the one which has, that represents this blue curve. Here the operational error will be the maximum. What we find is that compared to having noise in wire 1, it's much more detrimental to have the noise in this T-junction. So this T-junction is given by this yellow one. Similar results are, okay, so somewhat actually different results are found for this quantum dot. What we find is that for small noise correlation times, the dots seem to be quite robust, while if you have just the noise in the dot, while if for large noise correlation times, the dot seem to show an upturn. And this upturn could be due to some kind of detuning effect. What it is you're driving the noise really slowly, or in other words, you have kept the kept one of the potential in, or one of the level fixed in a level which is like unchanged. Okay, to conclude, what we find is that basically we studied finite time transport in piano key setup. We identified scaling laws and optimal driving regimes. We quantified deviations from ideal braiding due to finite time effects and noise. We find that in the tri-junction geometry, noise affects the junction region the most, while in the quantum dot geometry, we find that fast noise in the dot region has weak effect. However, for slow noise, quasi-static shifts of the dot dominate there. Okay, thank you for your attention.
For such a nice technical talk. So questions?
So I have a very general type of question, like Majorana is not a real particle, right?
Well, in high energy physics, yeah, I mean, okay, so in terms of if you ask what is its charge or what is its Mass, I think they are not defined here, but it's a mode, yeah.
So that's why I am asking. I mean, when you are saying moving Majorana from here to there, exchanging region, how can we think of these things really? How those sentences are
No,
meant to be?
so basically, you are saying where is this mode? Okay, so basically, the Majorana mode is always present at the edges of the topological superconductor. So if you are changing the region of this topological superconductor, you know where the Majorana mode is. Okay, and then if you say, okay, is there some kind of signatures of this? Yeah, I mean, you can do a tunneling measurements and stuff, and you can indeed see the signatures of those states over there.
And in the one of your
Okay, so however, when we are doing this overlap, we are not taking a single, how does a single Majorana mode evolves and comparing with the Majorana mode, let's say, which should be present here. What we are doing is overlap of the whole many body ground state, because when you're evolving things, everything is getting disturbed, okay? And so what you want to do is you want to basically take the overlap of the whole thing, because those excitations which are disturbed due to the, let's say, the vacuum, those will also cause decoherence, okay? So you want to know, you want to get a good quantitative idea of what caused the problem. Yeah, so it's not, we're not just focusing on this individual Majorana mode.
so one of your slide you were showing that either Majorana modes can be filled or empty.
Yeah,
So I mean there is two bump at the edges.
right.
So it cannot be happen that one is filled and other is empty.
Can you be a bit louder? It cannot happen?
I mean one end is filled and other end is empty.
No, no, it will be filled at the same time. It will be filled at the same time. Okay, so basically these two Majorana modes can couple and form a fermion. Okay, and you are basically asking whether the fermion is filled or not filled. So the representation is that the two, when you say the fermion is filled, you say, okay, the two Majorana modes are filled. If it's empty, you say the two modes are empty.